Okay. Um, I assume I'll just start going because I don't want to keep you guys up too late. Um, can you not hear? Can you hear me? Okay. Some people are saying they can, some. Okay. Also, hey Ed, if you want to request to be put on stage, I can pull you up. Oh yeah, you can. Of course.
Hello, hey, how's it going?
Hello. Hello. I'm good. How are you?
Pretty good. Um, I guess we can start in a little bit.
I was told that not Charles was gonna record, so I'm waiting for him to say.
Okay.
But otherwise, we'll just go ahead, and it is what it is.
Yeah, sure. I might be able to record myself actually. We'll see.
That would be great. Is Charles recording? He is.
Oh,
Oh,
okay.
oh, okay, okay, we can go. So, just a bit of structure. I'm gonna start by covering some basic content. I won't be spending too much time on it because you guys should be pretty good with content by now. And after each topic, I think I have one question for each topic. If not, it is what it is. And we'll do that question when I have a couple more questions. And then this will be for the SL content. And then once we finish the SL content, we'll go on to HL content and we'll do the same there. Okay? Okay, let's get started. So in let me just get my pen. Okay, so in electricity and electromagnetism, the main thing we need to understand here is wait, can you hear me? Can you still hear me?
Yeah, I think it's all good.
It's all good? Okay, sorry. Um, yeah, the main thing in electricity and electromagnetism is understanding the electric field because all circuits, essentially, what they are, is using the potential generated by uh, a power source to create an electric field that electrons flow through in completing a circuit. So, first of all, this is the IB definition of an elect. Wait, is that yeah, that is the IB definition of an electric field. Oh, my screen disappeared. It's back. And it's a force per unit charge experienced by a positive test charge. And it's important to note that a test charge is small and it does not influence the charge distribution in the field that it is in. Okay. And the first fundamental law of how charged particles interact with each other is Coulomb's law. And you guys should be pretty good with Coulomb's law. And Coulomb's law states that the force between two charged particles, I'll make my pen smaller later because this is huge. The force between two charged particles is proportional to the charge, so Q1 or Q2, and inversely proportional to the square of the distance between the two charges. This is very basic stuff. You can immediately see that there are parallels here between Newton's law of gravitation and Coulomb's law. And that's essentially because um, gravitational fields and electric fields are quite similar and they behave quite similarly. And we'll go into that a bit more later. And then the other thing to understand before we go into circuits is how electric potential energy is defined and what electric potential is. So, electric potential energy is the amount of energy given to it that a charge has given to its position within an electric field. So if you're in here, I have some diagrams of electric fields. And electric fields go from positive to negative charge, as we can see here. So any, oh no, what's happening? Okay. So any charged particle, I should choose a different color. Sorry. Any charged particle, and I should also be smaller. That's better. Any charged particle within this field will be assigned an electric potential energy because it's in the field. And electric potential energy, yes, is defined by the electric potential, where the electric potential is the work done per unit charge in moving a charge to a point in a field with respect with respect to a reference point. So let me just the electric potential energy is dependent on the charge as well as the potential as the electric potential at that point. But the electric potential is independent of the charge of the particle. Okay, so that's the difference between potential and potential energy in an electric field. And now, some questions that come up, let's just take an electric field, a uniform electric field with a positive plate here and a negative plate here, and a uniform electric field in this direction. And we have an arbitrary distance d. If we have a charged particle, in this case, a positive charged particle, and we place it inside this this field, by the time it travels a distance d, it will have gained it will have experienced a change in electric potential energy as well as electric potential, and that change in potential energy U will be manifested in the form of a change in kinetic energy. It's gaining kinetic energy. So let me just do this. And simply in a uniform magnetic field, a uniform electric field, the change in potential will be defined by E, which is our field vectors here, times D, and this will be our change in kinetic energy. And from there, you'll be able to solve for the velocity of the electron, well, the change in the velocity of electron given it starts at rest. After it's traveled a distance d in this electric field. And this is quite common. You'll see it in a lot of paper 1 questions because they want you to understand how this potential energy gets converted into kinetic energy when you're in a field. And yes, also a good thing to remember, I shouldn't delete that, I'm sorry. The good thing to remember is that force and electric potential, or any potential, really have a relationship, and that is that this relationship is more explored in topic 10, but it's good to have an idea of um, in general, in topic 5, and also in physics in general. It's that the electric field, E, sorry, there should be a Q here. Let me just, yeah, there should be a Q there. This electric field E is defined as the gradient of potential, and this is how the IB data booklet writes it. But essentially, the strength of an electric field is defined by how potential changes with respect to distance. So if you have a positive charge here, the electric field will be, if this is E, will be equal to the rate of change of potential. So if this is V1 and this is V2, and this is some very small delta R, and this is R, the change from V1 to V2 and in delta divided by delta R, and the negative of that will give you the electric field strength at that point. This is a bit of a terrible diagram, I'm sorry. Yeah, so that is that. And then I had something important to say here about electric fields around spheres. It's also, I remember there was one question about this, but it's quite tricky, and I don't know if it's going to be kept in the new curriculum or if it will come up anytime soon. But it regards the electric field produced by a hollow sphere, and in the case of a hollow sphere, no matter what the charge is on so let me just emphasize the fact that it's hollow. Hollow sphere. In the case of a hollow sphere, there is no electric field inside. And that is a consequence of Gauss's law. And Gauss's law states that the electric field inside the electric field produced by in some volume is related to the charge that lies within that volume. And if we see in here, there is no charge inside here. So being that there's no charge, there will be no electric field inside this hollow sphere. But if we look at the hollow sphere as a whole, if we say it is negatively charged, there is an electric field on the outside of the sphere. Because if we take the volume of the whole sphere, there is a concentration of charge. But if we look inside the sphere and we take an arbitrary volume inside the sphere, there is no charge in there. Yeah, parallel plates. We talked about between parallel plates, there's a uniform electric field, so it does not vary with wait, is there a uniform electric field between parallel plates? Well, it depends on the permittivity. We'll talk about that in the HL section. But yes, okay. Now, I guess, do we have any questions before we move on to the circuit section? I don't know. I can't see very well. No questions. Maybe in the other chat. Is there? No questions. Okay, please do stop me if you have any questions. I would have preferred doing this in general one, but I guess this is how it is. Okay. Now we're going to move on to circuits, and the first thing we talked about potential earlier, electric potential, and how if we have a battery, we have our positive plate and our negative plate. So essentially, if we look at what a circuit is, and we have some components here, a circuit is an electric field that follows this way. Because when we look at a battery and we're told the battery is a 9-volt battery, essentially what it means is that the difference between electric potential between this side of a battery and the other side of a battery is 9 volts. So the work done per unit charge in moving an electron from this side of a plate. So the work done by a unit charge when completing this loop will be 9 times the 9 volts, because it's the work done per unit charge. And if we remember here, I have the units. Work is in joules, and potential is in volts, and electron charge is some multiple of V. Joule is not equal to EV. This is just unit convention. But an electron volt is a unit of energy. It's because a volt is the work done per unit charge. So technically, a volt is a joule per coulomb, which is a certain number of electrons. I don't remember it specifically, but it should be in your data booklet. Okay. So yes, a circuit essentially uses a power source that has a potential difference, say 9 volts, to create an electric field within the wires and the components. And in creating this electric field, there will be a flow of charge. There will be electrons flowing in the direction opposing to conventional current. Conventional current here is what I'm drawing, because it's the flow of positive charge. It's not really flowing. Essentially, what's happening is the electrons are moving. In this example, the electrons are moving clockwise, so we could say it has the same effect as positive particles moving anti-clockwise. So yes, this is an IB definition that will be asked of you, and it defines current as a rate of flow of charge. And then this is just very basic stuff. I'll go through it as quick as I can. So Ohm was some guy, and he said something like the current flowing through a conductor is proportional to the potential difference across it. And what that looks like is that V is proportional to I, and that introduced some constant, not some constant, but some new thing that we call resistance, which is a measure of how a conductor allows electrons to flow through it. Higher resistance means that the flow rate of electrons, i.e. the current, must be lower. Okay. And again, the potential here, we can focus on a specific component, such as a resistor, and it has a current I flowing through it. The potential difference across this resistor is again the electric field that is pushing the electrons through it. So it's the same sort of treatment. Electric fields are everywhere, and once you understand this, circuits become a lot easier. And then the biggest tool in IB topic 5 is Kirchhoff's laws. You need to know these laws inside out. And so Kirchhoff, the first one is the voltage law. And essentially, what it is that the sum of potential difference drops across a circuit throughout the loop of the circuit must equal to 0. And why is that exactly? If we look at this battery, the potential difference across this battery here is, if we were to put a nice, I forgot the fucking, oh, my bad. I forgot, here we go. We put a nice voltmeter here. The voltmeter would measure 9 volts. That tells us that the electric potential of one side of a battery with respect to this other side is there is a 9-volt difference between it. So there must be, as we take the sum of all of the drops, and if we set one end of a battery as 0 volts, because remember, voltages and potentials are all relative to given points, there must be a drop of 9 volts. So if we're given 9 volts at the start, that must equal to, say we have a component here and another component here, and we'll call this R1 and R2. 9 volts will be equal to the drop across the first component and plus the drop across the second component. And this is an example. That's our first law. And the second law is, and keep in mind, this can be applied to any loop. So any loop you can form in a circuit, say you have a parallel circuit that looks something like this. Let's say you have a lamp here. You can form 2 different loops, and this is essentially what helps you in creating all those simultaneous equations we love Kirchhoff for, because you can form a loop here, you can form a loop here, and you can also form a loop in here. So you can form all these loops, and they all give you simultaneous equations in terms of i's and r's and whatever. And the last Kirchhoff loop law is that the sum of currents going into is essentially a law of conservation. Laws of conservations are everywhere in physics, and we love them because they make things work very easily. Essentially, what this law is that what current comes in must be conserved when going out. So if we have a junction that looks like this, I1 will be equal to I2 plus I3. And when these two laws are used together, a lot of simultaneous equations can be solved, they can be formed, and you can solve for pretty much all. Given enough information in the question, you will always be able to solve for all the voltages and currents and resistances if you're given enough information. Okay, and now we're going to look at EMF, which is, this is the IB definition, the energy difference per unit charge when completing a circuit. Or this is the one I prefer using, the work done per unit charge when a circuit is completed. Yeah, and the equation we have with regards to this is the internal resistance equation. And this is because EMF is used particularly in scenarios where we have batteries, and batteries always, in the realistic case, have internal resistance, and they look something like this. And what this tells us is that the EMF here, following Kirchhoff's loop law here, that the sum of voltages must be equal to zero, the EMF E, since little r and big R are in series, they can be summed for the total resistance. So this equation essentially looks like this, right? If we take big R to be the resistance of the rest of the circuit, excluding the battery, this is what this equation looks like. And I believe you get asked questions where you're given graphing questions and you're given a line that looks like this, and you are told to solve for the internal resistance. And to solve for the internal resistance, you simply wait. What is it? Is it that you're given? Yeah, you're given. It's a classic. I think. Oh, remember. You expand this equation into IR plus I little r, and then you are told what the battery is labeled as, and that goes here, I believe, what the battery is labeled as, and you have a linear equation in terms of I, and we'll have voltage here. I'm sorry, I'm tripping. You rearrange this, and it becomes E minus IR equals some voltage. And that voltage is this over here. And this will give you a graph that looks like that. And you essentially are then required to solve for little r. And you're also required to solve for E, which will be this. And little r will be your gradient. You guys know how to do that. Okay. Yeah. And that is that. Then another thing I forgot to write down here, but I have it in front of me. You guys are fine with adding up resistors, I assume. That is some basic stuff. We'll cover it in questions. Otherwise, resistivity. Resistivity is a measure of a resistance of a material. And yeah, essentially, you have this equation, and what you need to be very good at in exam is rearranging it very quickly and finding dependencies. So in paper one, for example, there will be a lot of questions that ask you for the ratio between two materials, the ratio of resistivity between two materials or two different wires, in which case you need to be good at rearranging this equation, finding to what variables resistivity or resistance is inversely proportional to, and then using that to determine how it will impact your ratio. You need to be very good at rearranging these fractional equations, because the IB likes them a lot. Okay, So I say we can look at some questions here. So this question was the first one that was sent to me, and it was sent to me twice, so it's quite important, I guess. Uh, and it is quite simple. I don't know. Do you guys want like a minute to attempt it yourselves, or yes, electron flow. I'm just reading the chat now. Electron flow is opposite to conventional current flow. I have that in the notes. I'll hand those over to you after the session. Uh, so do you want 2 minutes to attempt the question, or are we good? We go? We good. Okay. Okay. I'll go through it now quickly then, because I know Anne just wanted to cover it. Let me just go back. Okay, so this question, identify the laws of conservation that are represented by Kirchhoff's circuit laws. So we said before, this is the second law. The second law is essentially conservation of charge. Charge is always conserved. We see this even when we look at subatomic particles and very small things. Um, yeah, physics loves this law. So an example of this that's in the IB study guide for physics is that when you brush your hair, the static that is formed is only because electrons from your hair are getting moved onto the brush. So the charge of a whole system of you and the the brush. Oh, okay. I'll only look at the voltmeter part, but it's good to know this part too. The charge of a whole system, which includes the brush, will remain constant throughout the whole time of you brushing your hair. Okay. So yeah, we'll look at specifically the reader of a voltmeter. So here we just use Kirchhoff's loop laws, and to just it doesn't really matter which way you assign the current in Kirchhoff's loop laws, but it's always good to use intuition because it makes your working easier later on. So if we have 10 volts to 4 volts, the potential difference here is 6 volts, right? Because that's just simple stuff. That's not 6. But the potential difference between points A and point B, so VAB, is equal to 6 volts. Now that's just, well, it's equal to 6 volts. So that tells us that a good intuitive thought is that current will be flowing this way and through the battery this way. And if we remember correctly, um, an ideal voltmeter has infinite resistance, so there will be no current flowing through there. And that's actually how they measure the voltage, because no current is able to flow through them. We're able to see the difference between 2 points. Okay, now, so we start with our loop, and let's start over here. We have 10 volts at the start. and we'll call the current I. And if we remember Kirchhoff's first law, it's the sum of voltages is equal to 0. So 10 is it's going to be 10 minus, oh, why did it move? That's terrible. Move it up back. Order, center back. Okay. There we go. This plus all the voltage minus all the voltage drops. So then we can rearrange, and we're given that 10 is equal to, so the first voltage drop occurs over here, but since we're flowing opposite to the direction, we subtract 4, so the voltage drop would be 4 volts, so here it becomes positive. We just moved it to the other side. 4 volts, and then the other drop occurs at the 2 ohm resistor. So, sorry, let me add a line here. This implies that 10 is equal to V drop. Okay. And I times the 2 ohm resistor, and then we have our I times the 1 ohm resistor. And then we can simply do 10 is equal to 10 is equal to 4 plus 3I. And rearranging tells us that I is equal to 2 amps. And then to solve for the potential difference across these 2 points, we can do this either 2 ways. We can find the potential drop across this whole half over here, or the potential drop across this half, and you'll find that it's the same because of the symmetry of the setup. So, for example, if we use cell B, we get the potential drop because of cell B, so which is the same as, I'll call it Vm. So the V that's measured, this is Vm, is going to be equal to 4 plus 2 times 2, because it's the 2 ohm resistor times the 2 amps. So let me just keep the units there, so whoever's reading the notes alone will be able to tell. So that's 8 volts, and you'll see that it's the same as what we got up here. Use cell A, your V measured will be equal to 10 volts, and this time you are losing. There's a potential. So before, since the power source was acting as a 4-volt drop because current is moving in the opposite direction, but here the 10 volt is acting opposite to the resistor. They're not both. So the 10 volt is adding to the current, whereas the resistor is removing from the current. So signage here, I'm just going to do absolute. But the reason you get the opposite sign is because on one side, you're measuring from the positive terminal of a battery to the negative, and the other side, you're measuring from the negative to the positive terminal. That's what's going on. But yeah, you get your 10 volts from the battery, and then you subtract 1 ohm times 2 amps, and you'll get 8 volts as well. So you get an 8-volt drop across, measured by Vm. Okay, so that's that. I have another question here, which is an MCQ. This is very simple SL question. Uh, Same logic, really. But this time you're solving for EMF. So you use your EMF equation. And this is what it is. And you're told you're told the um, little r, and you're told big R. So it's just a question of subbing in, and you get plus 2, and you get E equals 6. Very nice stuff. So C is our answer. Most of these MCQ questions, this is just an exam tip, you want to keep under 1 minute 30 seconds. So as you go, if you're spending 1 minute on a question, start looking this isn't a hard question, but with harder questions, if you spend more than 1 minute on it, first of all, decide how much time you still have and whether it's worth spending more time on it, or if you go on, finish a test, and come back to it, that's also good. Otherwise, uh, if you still have no clue what to do after 1 minute, start breaking down the information that's given to you and see what options you can eliminate immediately. So, for example, here, you can almost instantly eliminate 24 volts because that's just a lot. And if you look at the size of our resistors, they're both quite small. And with the current here you'll have 5 volts, and here you'll have 1 volt. So 24 volts is out of this world. But yeah, okay. Now I think I have one more fields question. This relates to circular motion as well. I don't know if you guys have studied that, but yeah, so before, we knew that positively charged particles, they follow the electric field, because an electric field flows from greater potential to lower potential, always greater to lower potential. So a positively charged particle will follow the field. And if a positively charged particle is traveling a circular path, what do we know from circular motion when we travel a circular path? Let's see. Let's see the chat. What do we know about circular motion and circular paths? Anything. There's a centripetal force. Very good. Force towards center. Always. Very good. Very good. Good, good. So, in order for there to be a centripetal force here, we want the force vectors acting along this path on the positive charge to always be pointing towards the center of rotation. And in order for that to happen, which of these fields looks the most correct? Again, instantly eliminate these. And this. So you're left with one. Okay, this was okay. This question was maybe not that good. Okay, I think I'm starting. Oh, I didn't go through power, but I'm sure you guys will be fine with power. This question with Coulomb's law. This is a good question. So you have 4-point charges, and the IB likes this type of question with Coulomb's law. So you want electrical potential. Oh, this is unit time, but we'll do it anyways because we're like that. So electric potential is the basically it's same as the force because we're told, but this is the potential energy and the electric potential, which is equal to QVE. And this implies that VE is equal to KQ over R. So it basically does not matter what our charge is. Again, it's electric. It's the work done by the work done in moving a charge from a reference point per unit charge. So yeah. So for the square, uh, we have our positive charges here. First of all, very good thing to do is just identify the symmetry of a problem, and we should get that um, we should be able to use this R here to identify this R1, and then since it's a square and O is a center, we know that these distances are the same in each. So these are all R1s. Uh, okay, and then we just need to do two calculations here because we have two types of charge. The first one, so first let's solve for R1 so we can substitute into our distance part. So R1 is just going to be using Pythagoras, you get R is equal to R squared is equal to R1 squared plus R1 squared because it's an equilateral and not equilateral, it's an isosceles triangle. And isosceles triangles, very neat. You just solve and you get root 2 R. This is wait, am I getting confused? Yes, I am. This is R1. So R divided by root 2 equals R1. And this is what we want to substitute into our equation. So first we have our two positive ones, which are the same distance away. So that will be just KQ over root 2 plus root 2 KQ. Oh, I'm using big Q. I'm sorry. And then, so this is the potential at O. These are our two positive ones. So 2Q pluses. And then we have our negative ones, which are, if we look at this equation, that's just like sticking a negative sign in front of it. And they're the same distance again. So we get, this is like the rigorous way of solving it. You don't need to do all of this because, like I said, it's a very symmetric problem. And what happens here is that the fields from the right side and the fields from the left side cancel in potential, and you'll get zero potential there. But I'll just work through it for the sake of equations, and you'll see that we get 0 equals 0. It's A. Okay. But yes, again, use symmetry and you'll see that it's 0 before even having to do all of this. Okay. Should we do a power question too? The vector addition? Sorry, the last question, the circular motion one or the potential one? The potential one, vector addition. Well, potential is sorry, what am I doing? I'm on the wrong file. You can't see that one. Okay, so vector addition won't work here because suppose, first of all, uh, what you're thinking of is probably, I don't know, but what I assume you're thinking of is using the force. That wouldn't work here because there is a force. Whatever charge you'll be experiencing, so whatever force you'll experience will depend on the charge you have. And so, say you have a positive charge, you will be experiencing a force going this way. And if you have a negative charge, you will be experiencing an opposing force. Because what we're looking at here is not the force, we're looking at potential. And the relationship force and potential have, we talked about before, it's equal to negative gradient of potential. So the potential can still be zero, but it will have a gradient, right? If we use vector addition, um, yeah, it's because potential is not a vector. Force is a vector. So in potential will cancel in this scenario, but force will not cancel. The potential in a field is essentially assigning values. So we have A value, B value, C value, D value to all the points in this electric field. And the force experienced at point A, for example, will be the result of the gradient. So how fast potentials are changing. So if we mark this as A1 and A2 and A3 and A4, it's how fast potentials are changing with respect to position R at this point will determine the force you experience. But it has nothing to do. So potentials are not vector properties, they're scalars. So this is a scalar field, and um, therefore the only reason they cancel here and the force vector doesn't cancel here is because there is a slope, and the slope is if I draw this as a flat plane, and we have our q plus here and our minus q here, and let's have an imaginary graph here, and this is our potential and this is our position r. Our potential will be zero in the middle, but it still will have a gradient, so there still is a force. So adding with, yeah, potential isn't a vector property, it's a scalar property, and it's the force vectors that will cancel in the case, so this is a different field completely, in the case that there's no gradient. And there, that's a scenario where the force vectors will cancel. But in this scenario, that the question is asking about, the force vectors won't cancel. And in fact, we get a force going that way if we have a positive charge. I hope that helps. I know I was a bit confused. Okay, I'm moving. Do you guys want to go on to magnetic fields? Power question? Power question. We can do a power question. And then I'll move on to okay, I'll do a power question. In the circuits below, the cells have the same EMF and zero internal resistance. Resistors all have the same resistance. So we have our power equation, which is equal the power dissipated by a component or the power used by a component. Why 4 was added? Where was the 4? The 4 here, the 2 ohms and the 2 amps. Okay, that 4 was added because we solved for a current here, and we're told that it's 2 amps. And the 4 was added because the first 4 is the potential drop because of the cell. This is a power source. And then the second 4 was a result of Ohm's law being applied on this resistor. The potential drop across this resistor is 4 volts because we have a current of 2 amps. I hope that clears it up. About before? Okay. So, I just said that the first 4 is a result of moving in the opposite direction to this battery over here. We're moving in from the positive terminal and out of the negative terminal. So that will result in a 4 volt drop within itself. And then the second 4 volt drop is a result of Ohm's law being applied to this resistor. So we have a current of 2 amps going through it, and it's 2 ohms. So 2 times 2 equals 4 volts. So the drop across the whole cell here is 8 volts. That's what we did over here. Okay. No worries. I like questions. Questions make me feel like I'm being engaging, even though I'm not, and it's all an illusion. Power question time. Okay. Where was the power question? Oh, it was here. Okay. This is our power equation. So the power dissipated by a component in a circuit is equal to the potential drop across it as well times the current flowing through it. And the resistors all have the same resistance. Yes. So we know because of Kirchhoff's loop laws that the voltage drop across these two resistors is going to be the same. And we know that here they're also equal resistors. The voltage drop across them is going to be the same, but this time half of the total. Right? I hope that makes sense. But here we'll have half the current. This is I. And here we'll have the same current going through both. And okay, so honestly, the easiest way, this is just the easiest way to deal with this problem is finding the equivalent resistance. So here, the resistance, if they're the same resistance, it's going to be it's going to be a 2R, and then here they're the same. No, sorry, I'm tripping. R over 2. I was thinking about the other question. And here the resistance is going to be 2R, and the power dissipated is simply going to be power in circuit X over power in circuit Y is going to be equal to V I over VIX over VIY. The V's cancel because we're the same in both circuits. We have the same EMF. EMFs are equal. So then we just need to solve for the current. And what we get is that in circuit X, the current is going to be 2 times that in circuit, and here it's going to be, sorry, I'm really bad at explaining this, but here you have Ix and here you have Iy. If you're told that the two EMFs are equal, then you're told that I times Ix times Rx is equal to Iy times Ry. So if Ry is 2R and Rx is R over 2, we get Ix equals R over 2 times Iy 2R, and then this is an X, not a Y. And then we need to find the ratio. So we divide both sides by R, and we divide by I times Iy times R on both sides. And we get Ix divided by Iy is equal to, sorry, there's a 2 there, and there's a 2 there, which implies that Ix over Iy is equal to, whoa, what's happening? 4. And that is our last option. And let's see if there's a way we can get to it quite quickly. Well, you know for a fact that Ix will be, the current flowing in X must be greater than the current flowing in Y. And you know that the voltages are equal. So you know it will be a top-heavy fraction. And that eliminates A and B. The reason we know Ix will be greater than Iy is that the total resistance in Ix is a quarter of that. Well, yeah, of course, if you do the maths, it's a quarter of that of circuit Y. But also, series circuits, if you have equal resistors, are always going to be of higher resistance than a parallel circuit. So it's a top-heavy fraction that we're looking for, and the resistor in Y is a quarter. The total resistance in circuit X is a quarter of total resistance in circuit Y. So the current in X must be 4 times that of the current in Y, and that's how we can get to D quickly. Are we good? Okay, I'll explain it again. So obviously you can do all the formula here, but let's do it via reasoning. So the first thing always with these MCQs is identifying what you're looking for. So you're told that the EMF is the same, so you can instantly equate it. You go EMF of X is equal to EMF of Y, right? And what that tells you is that IX, which is this, why is my keyboard coming up? IX times the resistance in X is equal to IY times the resistance in Y. And the total resistance in circuit X is R over 2 because you do the series addition, sorry, the parallel addition of resistors. And in circuit Y, you do the series addition, so you get 2R. And then you just solve for the ratio. Let me see that ping. Is voltage being distributed in parallel being same and different in series? Sorry, I don't understand. Oh, as to why um, the current in X is larger? Well, it goes back to this. So the current in X is larger because EMFs are equal and the resistance in X is less. So since voltage is, uh, sorry, current is inversely proportional to resistance. If the resistance in X is less, the current will be higher. Agree? Perfect. Is there any way you could eliminate 2 without calculation? Yeah, that is the way. You say you figure out that in order for EMFs to be equal, um, the current in X must be greater than the current in Y. So you'll get a fraction that's greater than 1. So you eliminate A and B immediately. Got it? Uh, do you guys want a break or go straight into HL stuff? Straight into it? Okay, let's go. Let's go. This is my favorite part. I'm sorry if my explanation of all of this SL stuff was quite rusty. That's because, as you can probably tell, I haven't covered it in a long time. But this HL stuff will be better, hopefully. And also, if you're SL and you're still here, which, uh, in which case, great. We'll be doing all the hand signs or gang signs, as they call them, for magnetic fields, which you need to know for the forces acting on conductors. Yeah, yeah. You'll see me in the exam halls repping the Lorentz force. Okay, let's start. Electric. So, magnetic fields are electric fields, but with more swag. Okay, so what I mean by this is they describe how electrostatic forces behave when there's relative motion between two charges. So if any of you do relativity, there's a whole, it's eye-opening really. But essentially, magnetic fields are electric fields just plus relativity. And that makes them cool. Okay, and the main thing we deal with here is that, so here I put this very neat table that I copied from somewhere. And it explains what acts on, what each field acts on. And we'll see here that magnetic fields, they always act on electric currents. And that is because electric currents are essentially charges that are moving. Pretty cool. And what we deal with a lot in electromagnetism is this thing called the Lorentz force. And for those of you that know how to do vectors, we have our first component of a force, which is the normal electrostatic force, which is simply QE. And that was also here. This is the same because that's work done, right? QED is work done because this is force. Okay, that's our first component of a Lorentz force. And the second component is this, which honestly in IB physics you don't even worry about it, but it's the cross product of velocity and the magnetic field, and that describes the force experienced by a charged particle in an electromagnetic field. So yeah, okay, pretty cool. And electromagnetic fields magnetic fields are drawn from north to south. We go like this. Okay, good stuff. And they only act. So the main difference here is that magnetic fields only act on charged particles if they're moving. As you can see, if this velocity vector is a zero vector, there's no velocity. This whole term goes to zero. So you're only left with electrostatic forces. Okay, so forces on currents and charged things. These are SL equations, but that I forgot to talk about in the SL section. Luckily, there are no SL students and they didn't leave. That makes me very happy. So we have our first, this is directly from the data booklet. This is QV, the sine theta, where theta is the angle between the velocity and so the motion of a particle and the magnetic field B. This will be theta. Okay? And that is the thing that comes from, that is the force that comes from here. F equals QV sine theta. But the direction of that vector is dependent on the cross product. So it will be perpendicular to the direction. It will be perpendicular to the plane spanned by V and B. And that's just how the cross product works. If you do it in maths, it will make sense. And we have these hand rules that do it for you. But we'll go on to the hand rules after this equation, which is, why are we moving? F equals BIL sine theta. And it shouldn't be too crazy because why did that not work? Anyways, these two are essentially the same because QV is equal, more or less, is more or less equivalent to current. Well, the direction of QV is equal to the direction of the current. Then we have L there. And the L is there because current is dq by dt, correct? We established this before. So if current is dq by dt, that is how fast, how much electron, so coulombs, how many coulombs are moving through a certain area of wire or a certain length of wire in a second. So you can draw parallels between QV and IL. Yeah, and it's the same sort of force. Okay, now we have our hand rules. These are all the ones you need to know. So the magnetic field is generated whenever charge is moving or whenever there's a north and south pole. In the case of a current carrying wire, the magnetic field will be in this circular pattern around it. And this comes as a result of Maxwell's equations. In IB, you just take it as a given. And then you have this is the cross product thing I was talking about, where current is equal to QV. Yes. Yeah, it's equal to QV. In this case, yeah. So always remember that current is opposite to electron flow. Okay, very nice. And then this hand rule with the curl can also be applied with solenoids. This is called a solenoid. To tell you which direction is the north pole and the south pole of the solenoid. So here, this is a north pole, this is a south pole. As we said before, magnetic fields go from north to south. And how you do it is you take your fingers and you curl them in the direction of the wire. So you would curl your fingers going this way, your thumb would be somewhere here, thumb, and your fingers would be going around. Wow, I should do art. Yeah. So you curl your hand that way, and you know what way is north and what way is south. With solenoids, an ideal solenoid will have a completely straight magnetic field inside of it, and it'll be uniform. Okay? Good stuff. Ideal, let me just write this down. Ideal sol uniform B inside. Okay. And now should we do a couple of questions with these hand rules? Oh, okay. So the confusion about the hand rules, honestly, normally I don't teach hand rules for a reason because everyone does their own different thing. Um, but the motion hand rule, the one you posted, is essentially uh, doing this QV cross B thing. Uh, the direction of QV is the same. So direction is equal to the direction of I because the direction of I is the direction of flow of positive charge. And what you do with your right hand is you put your index here and your middle here. And your index is always the first term of a cross product, so it's QE. And your middle finger is the second term of the cross product, and that will result in a force going upwards. Um, the reason you get this hand rule as well using FBI, if we, as you can see, F will always be in the same direction, but we're assigning I and B into opposite directions. And what that means, okay, let me just, I might need to make this bigger. QV, which is equal to I direction. Um, um, okay, so if we rotate, you need a bit of imagination, but if you rotate this hand, you'll get the same. Yeah, is that cool? So they're the same. They're the same hand rule. Good stuff. Okay, so a couple of hand rule questions. Do it with whatever rule you're most comfortable with. Don't force yourself to use anything you're not comfortable with. Oh, sorry, sorry, Charles. That's okay. Okay, we'll do questions. Questions here. So, oh, that's I don't know how many electromagnetism questions I have, but okay, we'll do this one. An electron is traveling in the direction shown by the arrow, and there's a uniform magnetic field, and it leaves going that way. So, what is happening inside this region? Let's think in terms of, so now we also have a y component of velocity. Before we only had x. So that means that some acceleration must have happened. What do you guys think? Eight. Let's see. So, like I said, something must have happened in this uh, in this magnetic field. We know that charged particles that are moving experience forces in magnetic fields. First of all, the charge is negative here because we're an electron, and we know that we're receiving some velocity this way, and that means that in here we must have experienced a force that takes us up, right? Because we're accelerating upwards. Um, so now we use our hands and we point our I finger or our QV finger in the direction opposite to electron flow because we have a negative charge. And then we point our thumb in the direction of the force we want, which is upwards. So if we have I this way, F this way, then B must be, sorry, I'm tripping. Yes, B must be out of the plane of the paper. Okay? Midnight physics is a large commitment, and I appreciate it. I admire your commitment. I used the cross product rule, whichever hand you normally use. It depends. I use my left hand for this rule, but some people use their right hand. And yeah. If you use the right hand rule incorrectly, it goes into the paper. Remember to look at the charge of the particle. So here, the charge is negative because it's an electron. So our I must go the opposite way. So if you use your right finger, if you use your right hand, your index is your current, your middle is your magnetic field, and your thumb is your force. So in here, we have motion going this way, so V is that way, which means QV minus QV is like that, right? Because we have negative charge. Sorry, I'll keep this QV. Force is this way, so B must be out of the page, right? This is using on with your right hand, use index, which is I, middle, which is B, and your thumb, which is F. Okay? This is either topic 5 or topic 11. It comes in both. This is topic 5, I think, still. This is the force experienced on charged particles because of a magnetic field. In your data booklet, it's magnetic effects of electric currents. But I think these hand rules, honestly, they're in the SL section of textbooks normally, so it should be good. Why am I getting a DM? Oh, the direction of current. Well, we're not looking at current here. We're looking at QV, and QV has the same direction as current. So we know that QV. Sorry, I shouldn't. So electrons have a charge that's less than zero. It's negative, right? So what that means is that if we take our QV vector will point in the opposite direction to V. Does that make sense? How so? Because the charge is negative. Electrons have a charge that's less than zero. It's negative. So if we have a vector pointing in one direction, this is V, minus V will be in this direction. Okay? Yes, QV is also the direction of current. It's not the same thing, but it's in the same direction. Okay, should we do this question? This is a very good question because it combines electrostatic forces and magnetic forces. Should we? I'll give you like a minute to try and solve this one while I get some water. Okay, I'm back. So does anyone want to come up on stage and walk me through their thought process, or should I just go ahead? Okay, we lost one. That's terrible. Okay, I'll just go. So let's read the question. A positively charged particle enters the space between two. Blah 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 blah. with constant velocity. The top, okay. The particle continues to move in a horizontal straight line between the plates. Okay, so before we said that what forces will this particle experience? Well, it will first experience an electrostatic force because of the plates, and then it will also experience some magnetic force. Let me just simple plus F mag, right? Because of a magnetic field. And in this case, the magnetic field and the electrostatic field here, the forces induced by them must cancel because the particle is going in a straight line. And if we look at the direction of the electrostatic force, that will tell us about the direction of this. Make sense? Because they must cancel. So, for example, the positive charge here will experience a force going down this way, an electric force going down this way. So the magnetic force must be up. And it's a positive charge. So for the force to be up, we want a and a velocity going this way. It's a positive charge, so QV will be going this way. That's the same as current going that way. That means that B, oh my, F, we want F to be up, F of B to be up. And that means that B must be into the page, which is A, which is what you guys said. Good job. Yes. So if there were no magnetic field, uh, the electrostatic field, so E, which goes the electric field, that's E, means that the the particle is attracted to the negative plate. But we are we are told that it continues to move in a horizontal straight line. And that means that the vertical components of the forces must cancel. So QE must be opposite and equal to F mag. Okay. Yes. Equal in magnitude but opposite in direction. Are you sure? If you use your hand rules, I draw the little vector diagram in the bottom. It depends what hand you use. That's why I use the diagram instead of telling you what hand to use. Does that make sense as to why we want the magnetic field to be into the plane? Of course. So we want F to be opposite. We want FB. FB is equal to minus FE, right? The opposite direction. And in order for that to be true, we want the force uh, created by the induced by the magnetic field to be upwards. And we know that the velocity of a positive particle is to the right. So if force is up, velocity is to the right. Then that means that the field must be going into the page. Cool. Are you sure? Okay. Let's see. We have one more here. Okay, and this is instead using the other rule. I don't know if you still remember that rule, so we have. I'll remind you of these rules. Okay, and now we have this question here. So we want to find the direction of a magnetic field at point P. And since we know that this is a coil of wire, so it's essentially a wire arranged in a circle with a current going through it. And that means that a magnetic field will be formed. And if we do our right hand rule, we put our thumb in the direction of current and we curl our fingers, we'll find that our fingers go this way, which means that the B field will look like this. And that is carried on radially all the way to P. So the direction of P, of a magnetic field at point P, will be into the plane of the paper. Quite simple. I'll go back to the previous question with velocity after this. Yeah, I'm gonna fail is exactly right. So conventional current is the direction that a positive charge would move in. So I is in the same direction as QV. QV for a positive particle, if two particles are moving in the same direction, and one is positive and one is negative, QV will be in the same direction as V for the positive particle, but QV will be in the opposite direction to V for a negative particle. And QV will always be in the same direction as current. Does that diagram help? Okay. Now we're going to do electromagnetic induction. Very cool. Um, so I don't have a lot here, but electromagnetic induction is essentially the use of two laws. And these are laws that you need to know for IB examination. They like asking these questions. Oh, look at this. That's meant to be flow. Okay. So Lenz's law is the direction of an induced EMF is such that if an induced current were able to flow, it would oppose the change that caused it. So the current would create a magnetic field that opposes the change that caused it. Okay? And Faraday's law is the magnitude of induced EMF is proportional to the rate of change of flux linkage. And this is the equation that we get as a result of both of these laws. The flux is denoted by phi. This is the rate of change of flux, and n represents the linkage. You can pull n in and out of this rate of change because n is a constant with respect to time. You don't change. Unless n is changing over time, it doesn't matter. And the negative sign here comes as a result of Lenz's law. Because the negative sign means that this E over here will create a current in the direction opposite to this delta phi. Okay, and we have many more equations here to help because this concept is quite large. So first of all, what flux is. Uh, Sometimes it's called flux density. Well, simply, it's how much of a B field is going through an area. So we have BA cos theta. This is the equation that you're given in your formula booklet. And A represents this, say this is a circular region A. And then we have a magnetic field going into A. Here, A and B are completely perpendicular to one another. So is theta is actually the angle between B and the perpendicular to A. So if we have A like this and B like this, this is theta. I should use a much smaller marker, I'm sorry, but it can't change. Okay? And that determines your flux, your magnetic flux. So if your flux is increasing through a loop, for example, if your flux is increasing, then this term will be positive, and therefore your EMF will be negative, and you'll have a current that opposes the change made. So let's give an example here. I'll do the best I can. So if we have a loop like this, and it goes from a region of zero magnetic field to a region with more magnetic field. So this is our B. That means, oh no. Okay. And we'll have it like this so we can see what way the current is going. Initially, let's say there's no current. Initially, this is the initial state. So there's no magnetic field. I equals 0. B equals 0. Then we introduce a B. And then what happens here is that we get a current as a result that goes this way. And why do we get such current? Because this current, if we use our right-hand thumb rule, will produce a magnetic field that inside this circle, inside this area, will oppose the magnetic field that caused the current in the first place. Okay? That is Lenz's law in action. And yeah. Let me look at the chat. Okay, thank you for the session. Okay. Good stuff. We'll do. Should we do a question here? I don't remember if I have one on this topic. And I do not. But I could come up with one. Okay, I'll just finish and then I'll see how you guys are feeling and then we'll see. Okay. We still have more equations to go through. But essentially this equation, E equals minus n delta phi over delta t, can be, why does it keep on doing this? Okay, can be rewritten in many forms. So the first form is BVL, and this is essentially what this is. If you have a conductor of length L and it's moving at velocity v through a field, say the field goes out of a page B, in 1 second, the area it goes through, so dA in 1 second is VL, right? So this essentially, the change in area with respect to time. So dA over dt, where we'll write it with dA over dt is equal to VL. And then if we look at our equation here, where is it? Over there, we have that flux is equal to BA times cos theta. And if the perpendicular to area and the magnetic field are parallel, then cos theta becomes 1. So you get this. So if you BVL is equal to theta, sorry, I'm getting B times delta A over delta T equals BVL, and B times A equals this, implies that delta psi over delta T equals BVL. And there's no n in this equation because the conductor is a single, so there's no linkage occurring. Okay? So this is equal to the magnitude of EMF. And then you also have one more. When there is linkage, you just stick an n and it becomes NVVL. And that is, say, if you have a series of parallel wires all traveling through a field. Okay. Now we should go to capacitance. Very cool, very cool. So capacitors store energy in electric fields by accumulating charge. What a capacitor is essentially this. And what it does is it has a material in the middle that doesn't allow electrons to flow very easily. And that means that there's an accumulation of electrons on one side of the plate and an absence of electrons on the other side of the plate. And as you connect it to a power source, you get a voltage across these two plates, and that will start accumulating charge. And then as soon as you disconnect it and allow the capacitor to discharge, these electrons will flow in the opposite direction and help balance out the charges again on the plates. Okay, so that was a quick rundown of what a capacitor is. And now let's look at the capacitance equations. So like I said, the charge is proportional to the voltage across the plates. So if we have the higher the voltage across these two plates, it means that the higher the potential difference across the two plates, the higher the amount of electrons and the charge we have on one of the plates. Okay? And this proportionality, the constant of proportionality of this relationship, is called capacitance. So we have our first equation that Q, I think they use big Q. Oh no, they use small q. Q equals CV, where C is capacitance and it's measured in farads. Okay. And the thing about capacitors is that when you take the sum of them, they act opposite to resistors. And why is that so? Well, I'm glad you asked. Because I'll go through it now. So if we have a voltage here, we know that the voltage drop across these two capacitors must be equal to V. However, we also know that charge must be must be conserved. Wait a second. Someone's knocking. Sorry, I was talking and I forgot to unmute. Okay, so I'm back. And what it is that the charge, since charge is conserved, um, and these are of equal capacitance. Oh no, let's not say. Let's say this is C1 and this is C2. The charge must be equal across them because of the conservation of charge, which is also known as Kirchhoff's current law. So what that means is that the charge stored here must be equal to the charge stored here. And that tells us that Q1 is equal to Q2. And for Q1 to be equal, and then we also know that the voltage across our second plus the voltage across our first capacitor must be equal to our total voltage. And that is our second equation. Why is my thing tripping? And then our third equation is that I pressed Discord on accident. Our third equation is that the Q, which is equal to Q total, that's because charge conservation. And then our third equation is that Q total equals C total times V total. And V total is just V. And Q total is either Q1 and C total can be anything, and V total is V1 plus V2. C total. Am I doing it? Oh no, sorry. I'm doing this a different way. Then we know that Q1 over C1, which is our first one, is equal to V1, and Q2 over C2 is equal to V2. We know that these must add to V. So we have Q1 over C1 equals Q2. I won't do this for no one. This is taking too long. Plus is equal to Q total over C total. And then if we remember here, these are all equal, so they all cancel, and we get C1 plus 1 over C2 equals 1 over C total. And that's how it works. Okay. And then you can imagine that in parallel, they just add like normally, because voltage is conserved. Well, voltage is the same for each parallel branch in a circuit, whereas the total charge is a sum at that point, because you have the sum of charge from the first branch, the sum of charge from the second branch, and etc. Right? And so Q total will be equal to Q1 plus Q2 plus Q3, whereas voltages will be the same in each branch. So they essentially switch roles when you're in the okay. Um, okay, so capacitors when we charge and discharge. Oh, I should do this equation is also quite important, and it's the capacitance equation, and the capacitance of a capacitor is given by. Wait, I got a message. Okay, I got two. Oh, it was just yeah. Q is difference in charge over the capacitor. Um, no, Q is the charge stored in the capacitor. So you'll have a negative charge on one side and a positive charge on the other side. And Q is the charge stored. So it's like yeah, it's a charge difference between the two plates. Okay, I can go back to this now. So capacitance of a capacitor is determined by this equation, where E here is permittivity. Is it permissivity or permittivity? One of the two. It's the permittivity of the dielectric material that lies between the two plates. And the greater the permittivity, the greater the capacitance, which means that a greater a greater amount of charge will be stored per volt. Okay, so it means that electrons find it even harder to travel across the plates. Uh, wait, it's either that or the opposite. To be honest, I'm getting tired. But yes, and it's also inversely proportional to the distance between the two plates. So if you have two plates that are very close to each other, that means the capacitance will be quite large, which means that electrons will find it quite easy to go from one side to the other side. Whereas if you have a large distance between the two plates, capacitance will be low, which means electrons will have um, a harder time going from one side to the other side of the plate. Okay, and now we're down to 2. Wow. Now we should look at the charging and discharging equations, and this is the last thing I'll look at today. Because yes, this is the end. So capacitors charging. If we close this loop, current. Sorry, we're charging a capacitor. Or should we do discharging first or charging? We'll do charging first because it makes it's good to talk about. So then, when we close the switch, we're inducing potential difference drop from here to here. And what that means is that charge will be stored on positive charge will be stored. So conventional current is flowing this way, so positive charge will be stored here, and negative charge will be stored here. And when we close the switch, and this will happen until that's fully charged, and when we close the switch, current will flow this way in the opposite direction. And to solve for the equation of discharge, I wrote a little proof here, but I won't go into it. It's essentially Kirchhoff's voltage law to tell us that to allow us to use this resistor as well as the charge on this capacitor to determine how charge is changing over time. And then we get a differential equation for charge over time, and then we solve it. And we get our discharge equation, which is that our charge is equal to our initial charge times E over T time, divided by the time constant tau. And the time constant tau is RC, and that's in our data bucket. And that tells us that the greater RC is, the longer it takes for our capacitor to discharge. And this is the same for the inverse of this relationship. The smaller tau is, the quicker the time it takes to discharge. Okay, and this equation can simply be expanded to the I and to the current and voltage equations because we know the relationship. Well, we know that Q is proportional to V from this. And then because we know Q is proportional to V, we know that Q is also proportional to I because V equals IR. Okay? And since our resistance and our capacity, that means that this equation can be expanded into this equation and this equation. Okay. And Oh, scheiße. We need to also cover power generation and transmission. And that is the we need to do that, don't we? Since we're only two of you here, would you like me to go over um go over um what's it called? Transformers and rectification, all of that stuff? Okay. You know what I'll do? You know what I'll do? If it's not too bad for you guys, then I'll complete the notes myself and then I'll upload a note file um, with power generation and transmission as well. Number of people you're recording for is high. Also, thank you very much, Charles, for recording. Because, yeah, it's been 2 hours, that's what I'm saying. I'm fried. I was fried before and I'm fried now. So it's okay, short review, short review. Um, yeah, it's rough out here. Short review of power and transmission. I'll do this all by hand. So, um, power and transmission. So the main concepts you need to know in HL is how a transformer works. And a transformer, it's drawn something like this, I think, most of the time. And oh, why is there an arrow there? Okay, we'll say that the current goes this way. Um, there needs to be AC for current to work. For this type of power transformation to work. And basically, what it does is that it uses this alternate current to create an alternating magnetic field here. So B is alternating. And what that alternating magnetic field, so that magnetic field is generated by our um, hand rules, for example, like the current around the magnetic field induced because of a conductor and a current flowing through a conductor. So that's a magnet. Normally a metallic core they talk about, and it's laminated, and it's an iron core, right? Yes. And that iron core helps carry this magnetic field. And what this alternating magnetic field does is that it um, induces an EMF in the second coil such that it opposes the change of a magnetic field. Again, um, looking back at Lenz's law. So the alternating magnetic field from the AC source will create will induce an EMF in the secondary coil such that it opposes the change of a magnetic field that caused it. Okay, so that is a rundown of how it works, and now for the amount of loops and whatever, all of that cool stuff. So if you have so your voltage in the primary is going to be equal to like the rate of change of flux here, right? That's just applying Lenz's law. And the rate of change, and in the second coil, you'll have E secondary is equal to minus N delta psi over delta T. And these phi's are relative. So this is primary coil, this is secondary coil. We can't really actually we sort of these ends, sorry, not the size are the same, because we can assume that here locally the magnetic field is similar enough. So in our primary coil, we have P turns, and in our secondary coil, we have S turns. So E primary over E secondary equals NP over NS. And that tells us that the EMF here, so EP, is, and then here we have NP, and here we have NS, and here we have ES. We can figure we can figure out the equation for current using power. So power needs to be in an ideal transformer, power is conserved. But okay, this is a good thing to know for exam, because sometimes they ask it. Power loss is often due to heat in the iron core of the transformer and inefficiencies, which generate like electromagnetic field inefficiencies. And that means that not all of the power is converted efficiently. But in the ideal case, you get that the power in the primary coil is equal to the power in the secondary coil. So you get EP IP is equal to ES IS. So you get EP over ES equals IS over IP. Okay? Because power is constant in an ideal scenario, and if power is constant, voltage and current are inversely proportional. Okay? Let me open Discord. Okay. Is that good? Good stuff. And now we're going to do RMS, and I'm going to cover this even quicker. Even quicker, we'll do RMS. So when we have alternating current, this is going to be brilliant. Why did it do that? Okay. Is it not working? Perfect. So let's just say we have this is I and this is time. Okay, so we have both positive and negative current, but what we're saying is that in power generation, if I were to ask you what the average power generated in, sorry, ignore past this, the average power, the average current here, you would tell me it's 0. But that is not the case, because you always have some current flowing through the wire. It's just that sometimes it's equal to 0. So if we take the absolute average, what we get is this thing called root mean squared. So we square all the values, and we take the mean of it and we square root it. Okay? Very, very simple what RMS is. And that gives us, if this is I naught, that will give us an RMS value, I RMS, that is representative of the average voltage in that period, the average current in that period. And the same thing is done for voltage, since V is proportional to I, so we can do this. And since V is proportional to I, resistance is the same. Resistance is a constant, a positive constant. So as expected, it doesn't change over time, even if current and voltage are going positive and negative, positive and negative. Power, on the other hand, the average power, since current and voltage are proportional, what you'll get when you multiply, okay, I'm gonna try drawing it in the voltage graph in another color. So we'll get the voltage that looks like this. It's a bit higher amplitude, but this is V naught. What you get is that the power is always positive because you multiply two negatives and you get the positive. So its power will always be positive, and the average power will simply be V times I naught. This will give you the maximum power because that is taking this point and that point. However, the average will be half of V naught I naught. And this is because if you take root mean squared of the squared sine, because essentially you get a squared sine here, or a squared sinusoid of equal period, you will get a factor of a half. Okay? I hope that makes more sense. So the root mean squared of the sine squared is just equal to, it has a factor of a half instead of factor of 1 over square root 2. Okay. Okay. I think that is it for power generation and transmission. Do you guys have any questions? If you want, you can stop the recording and